So we can start talking about chapter 3. Most of the concepts in chapter 3 are almost the same as chapter 2. So chapter 2 was about normal stresses and shear stresses, but chapter 3 we will only focus on normal stresses, and normal stresses are also called axial stresses. So we already know how to calculate stresses. We already know how to calculate elongation or strain, which is change in length over original length. So what we will talk about is what is a statically determinant system and what is a statically indeterminate system. So in this book, they have given a definition for statically determinate system. So statically determinate system is a system where you have same number of unknowns as you have equilibrium equations. So if you have same number of unknowns and the equilibrium equations, you can calculate the unknowns. The unknowns in this case are the reaction forces, reaction loads. So if you have three reaction loads and you have three equilibrium equations, so you can calculate all the reaction loads from the equilibrium equations alone, and then this type of system is called a determinant system. But if you cannot solve the reaction loads, all the reaction loads, by using equilibrium equations alone, then this type of system is called indeterminate system. And I think in statics, you guys have studied about like what is determinant system and what is indeterminate system a bit. Okay. So in statics, we know it was an assumption that the body is rigid, it's not going to deform, right? But in mechanics of material, we have studied deformable body mechanics. We can calculate deformations. We can calculate stresses and strain. So from the knowledge we gained in mechanics of material, we can generate new equations to solve the indeterminate system. So these new equations, which we can generate by using the knowledge we have gained from mechanics of material, so these equations are called compatibility equation. So whenever you have an indeterminate system, you can still solve the indeterminate system by using the information regarding elongations and stresses. And when you're using the information from mechanics of material, then to generate those equations to solve the indeterminate system, then these equations are called compatibility equations. So that's the only new thing in chapter 3. And we can solve some examples in chapter 3, and then we'll see how, if a system is indeterminate system, how we can solve even indeterminate system by all the concepts you have studied till now. So we can maybe draw, to make it more clear, we can draw a simply supported beam. So if this is a simply supported beam and you have some external loads, let's just say this is 100 Newton, this is 50 Newton. And in this case, the reaction loads would be this. So if this is A, this is B, this would be A of Y, this would be A of X, and this would be B of Y. If we assume this is X axis, this is Y axis, and this is Z axis. So you have how many unknowns? You have three unknowns, right? You have A of X, you have A of Y, you have B of Y. So you have three unknowns. And how many equilibrium equations you have? You have summation of f of x is equal to 0. You have summation of f of y is equal to 0. You have summation of moment is equal to 0. So you have three equilibrium equations. So you have three equilibrium equations and you have three unknowns, so you can easily solve this system. So you can solve the reaction loads by using equilibrium equations. So if you can solve the reaction loads by using equilibrium equation, then this system, if I call it a system, then this system, it is a determinant system. And why it is a determinant system? Because you could solve all the reaction loads you needed to solve by just using the equilibrium equations. So if you can do that, then this system is called a determinant system. But what happens, let's take another example. So what happens if I make it a fixed support and keep the load same? So in this case, if this is A, if this is B, so this is a fixed support, right? So you have AY, you have AX, and then you'll also have a moment, M at A. And you will also have a reaction force, BY. So now we have four unknowns. And how many equilibrium equations we have? Three equilibrium equations. So we have more unknowns than the equation. So if you try to use equilibrium equations and if you try to solve this system, you wouldn't be able to calculate all the reaction loads because you have more reaction loads than the equilibrium equations you have to solve. So this type of system, since you cannot solve the reaction load, you can try to solve using summation of all the forces, but you wouldn't be able to like calculate all the reaction loads. So in this case, this system is called indeterminate system. So only if you use the equilibrium equation, you wouldn't be able to solve, but you would be able to solve this by using the knowledge we have learned in the mechanics of materials. So from the mechanics of material, whatever we discussed before, you're gonna generate some new equations from the mechanics of material, and those equations are called compatibility equations. So if you can generate one more equation, you just need one compatibility equation as well in this case. So in this way, you will have four equations, four unknowns, and then you would be able to solve the system, this indeterminate system. So whenever you get an indeterminate system, then you can generate new equations from whatever we have learned before. And whenever you use the knowledge from mechanics of material to generate new equations, then that equations are called compatibility equations. And we're going to see how we can generate new equations. So we can we can do some examples. So example 3.1 says you have two right circular cylinders loaded in uniaxial stress configurations. So if I draw a member, so this axis is called longitudinal axis because this is along the length of a member, so this is called longitudinal axis. And this force, there is a force, this force is called axial force. But it's the same as normal force. I mean, you can call it normal force, you can call it axial force, but why some people call it axial force? Because if the force is acting parallel to the longitudinal axis, then this force is called axial force. But it is the same as normal force. This is a normal force as well. And the stresses you're going to get from this are called axial stresses or normal stresses. And we have already talked about what normal stresses are, how to calculate the normal stresses, which area to consider when we're talking about normal stresses. So let's try to solve this example. So we have considered two right circular cylinders. So the modulus of elasticity, in the exam I will give you modulus of elasticity. So in this example, the modulus of elasticity is 10 raised to the power 7 psi. So it's in uniaxial stress. So uniaxial means the load is only along one axis, uniaxis. Cylinder 1, this is cylinder 1, this is cylinder 2. Cylinder 1 is, the length is 10 inches, this length, with an initial diameter of 3.3 by 4 of an inch. So I'm going to draw, this is cylinder 1, this is cylinder 2, and the diameter for cylinder 1 is 3 by 4 of an inch. And the diameter for cylinder 2 is 1 by 4 of an inch. This is T2. The cylinders are loaded with axial forces. The forces which are acting along the axis are called axial forces, as shown here. So P1 is 400 pounds and P2 is 600 pounds. So the first question is, either the system is determinate or indeterminate. So if you have some experience, even by looking at the problem, you can figure out that the system is determinate or indeterminate. But if you cannot figure out from the figure, then we can try to solve this. So if we can solve this, if we can get the answers, if we can calculate all the reaction loads, then we will be confident that this system is a determinate system. But if we cannot calculate the reaction loads, then the system would be an indeterminate system. How many you think that it's a determinate system? How many you think it's an indeterminate system? Okay, so let's see, let's try to solve this. If we can solve this, then it's a determinate system. So let's draw a free body diagram. So this is a fixed support. And you have two loads. One load is P1 is equal to 400 pounds. Another load is P2, which is 600 pounds. And then because of these, you will have reactions. So it's a fixed support, so you will have three reactions, right? If I call this A, you're going to have AX, you're going to have AY. If this is X, well, let's just name it accordingly. So this is it's okay, X, Y, Z. So this is AY, this is M, moment at A. If we assume this is X axis, this is Y axis, this is Z axis. So if you do summation of f of x is equal to 0, you're going to get a of x is equal to 0, right? If you do summation of moment at a is equal to 0, if you take a moment at this point, we can take a moment at any point, but if you take a moment at any point, all the forces have a moment arm 0. So you're going to get moment at a is equal to 0. If you do it, you're going to get 0. If you do summation of f of y is equal to 0, then a of y would be equal to 1000 pounds. If you use the equilibrium equations from the assignment 1 you guys have done. So you can solve this, and you can see we were able to solve all the reaction loads. So we had no problem solving the reaction loads. So we can safely say that it is a determinate system. Part 2 is we have to calculate stresses, normal stresses. So what is the formula for stress? Formula for stress is force over area, right? But what is this force? This force is actually the force which is inside the member A and the force which is inside the member B. That's the force. If we can calculate that force, we can calculate stress. And how we can calculate the force which is inside, like the internal load. So now we know what the reaction loads are. Now we have to calculate the internal loads. And we can calculate the internal loads by, cutting the section and exposing the internal loads. And once we expose the internal loads, then you can use equilibrium equations to calculate the internal loads. And that's the force which we're going to be using to calculate stresses, like we have discussed before. So I'm going to draw a free body diagram again here. So we have already calculated, we already know this load P1 is 400 pounds. This load P2 is 600 pounds. And we have already calculated the reaction load, which is AY is equal to 1000 pounds. Now we need to calculate internal load. So this is cylinder 1, this is cylinder 2. So in order to calculate the internal forces, we need to cut a section. So if we make a cut here, we're going to expose internal loads from the member 1. If we do a cut here, we're going to expose the internal loads in the member 2. So let's draw cut 1 here and let's draw cut 2 here. So imagine if we do an imaginary cut at 1, so we can expose the internal loads, and this is what we're going to do. So we have to calculate these forces, force F1 and force F2. Once we can calculate the force, then we can calculate the stress. So how we can calculate the force 1? So we can use equilibrium equations to solve the force. So let's use this part of the section and let's do summation of f of y is equal to 0. So you're going to get ay minus f1 is equal to 0. So f1 is equal to ay, and f1 ay is 1000 pounds. So you can calculate f1 this way. Here also you can use either this part or this part, I'm going to use this part because it seems easy. We're going to use summation of f of y is equal to 0. So F2 is equal to 600 pounds. So the question was to calculate the stresses, right? So we can calculate stress in the cylinder 1, which is F1 by A1. Force is 1000. Area is pi by 4 d square, which is 3 by 4 inches whole square. So stress 1 is equal to 2263 psi. We can also calculate stress at member 2, which is force 2 by A2, and the force is 600 pounds. Area is pi by 4, 1 by 4 whole square. So the stress in the member 2, in the cylinder 2, would be equal to 12223 psi. So whenever in the exam I ask you to calculate stresses, you don't have to use external loads, you don't have to use external forces, you have to calculate the internal forces, and then you have to use those internal forces to calculate the stresses. Because internal forces are resisting the external loads. So that's going to cause stresses, and those are the stresses we have to calculate. Now the third part is we have to calculate elongations at the end of cylinder 1 and cylinder 2. Elongations. And what is elongation? Delta is an elongation. How we can calculate elongation? So we know modulus of elasticity is stress over strain. We know stress is force per unit area, but I'm going to just use P. You can use any letter. Force per unit area. Strain is change in length over original length. So if you put stress in this equation and strain in this equation, then modulus of elasticity would be equal to, instead of stress, I've used P over A. Instead of strain, I've used change in length by original length. So you can take elongation on one side and all the other variables on the other side. So elongation would be equal to PL over EA. And this is a very important equation. You should like write it down or remember it. So this is like whenever someone asks you to calculate elongation, you can just directly use this equation PL over EA. But how you can calculate or how you can determine this equation is by using equations you already know. You already know modulus of elasticity, which is stress over strain. You already know stress, which is force per unit area. You already know strains, which is change in length over original length. So if you equate the value of stresses and strain in modulus of elasticity, you end up getting this equation, which is one of the most important equations in mechanics of materials, which is PL over EA. So you have to calculate elongation for cylinder 1 and cylinder 2. So I'm going to use cylinder 1 equation here, which is, so what is P in this case? In this case, P is F1 L1 over E A1. And for cylinder 2, the equation is F2 L2 over E A2. F1 in our case was 1000, length is 10, modulus of elasticity is 10 to the power 7, area is pi by 4, 3 by 4 whole square. force is 600, length is 10, modulus of elasticity is 10 to the power 7, area is pi by 4, 1 by 4 whole square. So elongation in cylinder 1 is equal to 2.26 into 10 raised to the power minus 3, or 0.00226 inches. And for delta 2 is equal to 0.01222 inches. Yes. P is a force, yes. But we have to decide which force this is. So this force is, so if we are talking about like cylinder 1, so this force is like the internal uh, load. So that is F1 in our case. So I just use P just like because most of the books they use PL over EA as an equation. So that's a generalized equation. We have to decide which force is P. So now we can jump to example 3.2, and like the rest of you guys who have finished this, you can read example 3.2, and we're going to do example 3.2, and we will see if this example is a determinant system or an indeterminate system. So it's exactly the same problem, but the supports are a bit different. So there's another, so the constraints are different, and we will see how we can solve this problem. Example 3.2. Let's go to example 3.2. So it says, so modulus of elasticity is 10 raised to the power 7 psi. So it says two circular cylinders confined between two rigid plates. So now we have a fixed support at both the ends. So cylinder 1 is 10 inches, like same like before. Diameter is 3 by 4th of an inch like before. Cylinder 2 also the length is 10 inches and the diameter is D2. D2 is 1 by 4th of an inch. Loading is different, so the force is 1,000 pounds. So now we have to figure out if the system is determinant or indeterminate. So how we can figure this out is we can try to use equilibrium equations, and if we can solve the system, if we can solve the reaction load by using equilibrium equations, then the system is determinant. If we cannot, then the system is indeterminate. So let's just draw a free body diagram. So we know the load is 1,000 pounds, and we know the reaction forces. I'm gonna draw the, let's just say this is point A, let's just say this is point B. There are no external loads in other directions, so I'm not gonna like draw the reaction forces, but you guys can draw. But I think these are the, because the load is on the y-axis, so I'm only drawing the reaction forces along the y-axis. You can draw another, you can try to calculate, but it's gonna be the same. So I think that's the most important. So I'm just drawing because there are no external loads in other direction, only on the y direction. So I've only drawn the reaction forces along the y direction to make it easy, but you can draw in other direction as well. So if you try to solve this, you can solve this by using summation of f of y is equal to 0. And you have fa plus fb minus p1 is equal to 0. So fa plus fb is equal to 1,000. So if you will use summation of forces along x-axis is equal to 0, so you cannot solve f of a, f of b because it's not along x-axis. If you try to take moment, the moment arm is 0, so you're gonna end up not solving. So you can like go back and you can use all the, you can try to solve this system, but you cannot solve the reaction forces in this case because along the y-axis you have two unknowns and you only have like one y-axis force. So if you try to solve the reaction loads by using equilibrium equations, you cannot solve the reaction loads. So since you cannot solve the reaction loads, so this is indeterminate system. It makes sense why it is indeterminate system. Okay, so now what we have to do is we have to calculate, the second part says determine stresses. So in order to calculate stresses, we need to calculate internal loads. And to calculate internal loads, we need reactions. But we cannot calculate reactions because it's an indeterminate system. So what we need is we need another equation to solve this indeterminate system. And that equation is going to be coming from the compatibility equation, from the knowledge we already have from the mechanics of materials. So we'll see how we can do that. But let's just try to like solve the internal loads. So if we have, so we need to calculate stresses, and for stresses we need force. And this force is the force which is inside the member, the internal force, the internal load. So how you can calculate the internal load is by making cut. So if you take a cut in cylinder 1, you're going to expose internal loads from the cylinder 1. And if you make a cut in cylinder 2, you're going to expose the internal loads from the cylinder 2. So let's try to do this. I'm going to write cut 1 here. I'm going to write cut 2 here. So these F1 and F2 forces are the one we are like interested in. So if we can calculate F1 and F2, we can use this F1 and F2 and we can calculate the stress. But in this case, it's difficult because we don't have a reaction loads. Once we have a reaction load, then we can use equilibrium equation to solve. But now it's a little complicated because it's an indeterminate system. So let's try to solve for F1 and F2. So I think we can use this part of the section and we can do summation of forces equal to 0. So FA minus F1 is equal to 0. So F1 and FA are equal. So if we can calculate the reaction, we can calculate the force. In this, let's use this part of the section and let's do summation of forces along y-axis equal to 0. So you have FA minus P1 minus F2 is equal to 0. So FA minus F this load is 1000 and this is F2 is equal to 0. So we are not interested in FA, we are interested in F1 and F2. So we can formulate this equation so that we only have F1 and FA. So we can put this value here. So we're going to get F1 minus F2 is equal to 1000. So that's one equation. F1 minus F2 is equal to 1000. This is coming from equilibrium equation. But we need another equation similar where you have F1 and F2 so that you can equate in here and then you can calculate for the internal loads. So let's try to use the knowledge we have from mechanics of material. We're going to generate a new equation. We're going to call this equation compatibility equation. Because we need one more equation to solve the system. So let's see how we can generate one more equation. So I'm going to draw a free body diagram again. We know there is a load here. That force is 1000 pounds. So imagine what this load would do. This load would deform this system and it will produce elongation. So if you try to draw the elongation, how this would look like, if there's a force which is like pulling this system down, so you're going to have increase in elongation here, and then you're going to have decrease in elongation in the cylinder too. So the system will deform something like this. This is our elongation. It makes sense, right? I mean, this is fixed, so this thing cannot move. So if you apply a force here, so this cylinder 1 will elongate a bit, and by the same amount, this cylinder will be reduced. So can I say that elongation in cylinder 1 is equal to the elongation in cylinder 2? Because both elongations are same. It's being elongated, so I've put a positive sign, but this elongation for system 1 is exactly the same elongation for the system 2, for the cylinder 2. So both the elongations are actually the same. But It is positive because it's being elongated, and the cylinder 2 is being compressed, so it's negative. So this is a compatibility equation we generated from the concept of deformable body mechanics. We know we will have deformations, and we can see the deformations are the same for cylinder 1 and cylinder 2. So I can write this down. This is from deformable body mechanics, from mechanics of material. We know the deformations are same. Does it make sense? Okay. So we know what deformation is. PL over EA. That's the formula for the elongation we generated, like we determined before. So in this case, for cylinder 1, the internal load is F1, L1 over EA1, and for delta 2 is F2, L2, EA2. So this equation is called compatibility equation. So now we have one more equation, and now we can try to solve the internal loads. So the modulus of elasticity is same, it's going to cancel out. The length are same, it's going to cancel out. So F1 is equal to negative A1 over A2 F2. We can put this value here. So it's going to be negative A1 over A2 F2 negative F2 is equal to 1000. So now we have F2, we can put the value here and we can calculate for F1. So now we have internal loads. Now we can calculate the stresses. The third part is to calculate elongations. That is delta. So for our case, we'll do F1 L1 over EA1. You can use either of the equation. So delta would be equal to, I'm going to use this part, F1 L1 over EA1. Force is 900, length is 10 inches, E is 10 raised to the power 7, area is pi by 4, 3 by 4 whole square. So delta would be equal to this. I think the force is 100. F1 is, yeah, okay.